Welcome back to the video lecture, and now we'll be continuing with the predicate logic rules of inference. So as I've already said you, rules of inference, we have got three rules. One is rule P, rule T and rule CP. So rule P is as and when we need the premises, it will be inserted, and we'll give the explanation as rule P, and then we'll be simplifying using the laws of implication and equivalence, and that will be denoted as rule T. And finally, we have rule CP, that is, if we think that if any of the premises is missed out in the given statement, and only if you have that premise, if we could able to get the conclusion, then we can add a newly premises can be added, which means that rule CP is new premises can be added into the statement in order to get the valid conclusion of the problem. So this is what we mean by the rules of inference. And also, apart from that, in the predicate calculus or in the first order logic, we have four more rules called as universal specification, universal generalization, existential specification and existential generalization. So all these we have seen in the previous session. So now that we will see how to get the conclusion or how to get the result of this given statement. Every living thing is a plant or an animal. John's goldfish is alive and it is not a plant. All animals have hearts, therefore John's goldfish has a heart. And we will have to check out whether the given argument is valid or not. So how do we check out whether the given statement is valid or not? So first thing, we will have to identify the keywords. After identifying the keywords, then we will have to assign the predicate terms. After that, we will have to frame the premises, and then we will have to see to that whether the conclusion part of the problem is arrived or not. So if we are not able to arrive the conclusion part, then it is an invalid statement. If we could arrive the conclusion part of the problem, then it is a valid statement, right? So now let us see here. Every living thing is a plant or an animal. So now we will have the solution part, that is, let P of x means x is a plant. X is a plant. Then animal also we have plant, animal, John's goldfish, and also animals have hearts. These are the four keywords we have identified it. And next is h of x, x is an animal. Then hearts, or we can have John's goldfish. So John's goldfish, it is a specific thing, it is not generalized here, it is a specific. So I'll goldfish, it is John's goldfish. John's goldfish. H of x, x is an animal and it is not a plant. All animals have hearts. So we will have the notation in a different form. I will have it to be as, let P of x, x is a plant. Let me denote this to be as A of x, x is an animal. Then goldfish, G to be as John's goldfish. And all animals have hearts, that is H of x to be x has a heart. Right. So these are the keywords we have identified it, and now we will have to frame the premises. Every living thing is a plant or an animal. So every living thing, what is a suitable quantification we will be making use here? It is the universal, since because we have got the word is every, so it is true for everything. So which means that for all x, every living thing is a plant or an animal. P of x is a plant, A of x is an animal. So every living thing, x is a plant, which is a living thing, right? So P of x, or here I have disjunction, so then it is A of x. Then John's goldfish is alive and it is not a plant. I have represented G to be as John's goldfish, right? John's goldfish is alive and it is not a plant. So plant is, we have denoted to be as P of x. If it is not a plant, it is negation of this, and x represents to be a plant. And here what we have said that John's goldfish is alive and it is not a plant. So which means that the predicate term here is not a plant, not P of G, right? So John's goldfish is alive and it is not a plant. So this is what all animals have hearts. So all animals, which means that we have here for all x, all animals have hearts. So if it is an animal A of x, then definitely it will have heart, right? So fine. So if it, which means that it is an if and then condition. So this should imply therefore John's goldfish has a heart. John's goldfish, it is G, has a heart. We have to denote it to be as H of G. Therefore, John's goldfish has a heart. So this is how we will be denoting it. So this is the premises out of which we have got from the statement. And now let us see whether the given statement is valid statement or an invalid statement. So we have serial number, statement, then the explanation part. So first thing is that we will take this for all x, P of x or A of x. First thing is, since because this is taken as it is rule P. And the second thing is that before we apply any of the logical laws and implication, we will have to remove the quantifiers if any. So I'll have to remove this quantification symbol. So which means that what is this your quantification called? It is universal. So universal quantifier, if I want to know it has been generalized, I'll have to specifically point out. So it is universal specification on 1. So I'll have to change it to a specific point, and the specific point here I've taken to be as G. So therefore it is P of G or A of G, right? So now this I can make use of the conditional statement and write it as, that is, if I have P or Q, this it is equivalent in writing it as negation P conditional Q. So this I can write it to be as negation P of G conditional A of G. This is conditional equivalence on 2. And next is, we have been given with one more premises as negate P of G, that is rule P. And now for these two I will have to make use of law of detachment, right? So law of detachment is what? If I have P comma P conditional Q, this will imply Q alone, law of detachment. These two are same. Likewise, these two are same. So which means that we will get this to be as what? A of G. Good. So now this is law of detachment. Law of detachment on 3 and 4. And next is for all x, A of x conditional H of x. Here we have rule P. And again I will have to remove of this. So in order to remove this quantification, we will have to specify it. So that is US on 6. We get it to be as A of G conditional H of G. So next is again detachment I will be making use for 5 and 7. So detachment, law of detachment says that whenever we have P and P conditional Q, it can be written as Q. So now this I can write it to be as H of the G. That is what the conclusion part of the problem. So therefore the given statement is valid. So this is how we will have to check out whether a given statement is valid or invalid. I repeat it. First thing, as soon as a statement is given and if we are asked to check out whether it is a valid statement or an invalid statement, we will have to identify the keywords, then we will have to assign it with the predicate terms. After assigning it, we will have to frame the premises, and we will have to see to that whether we are in a position to get the conclusion of the problem or not. If we are able to get the conclusion of the problem, then the given statement is valid. If it is not, if you are not getting the conclusion part, then it is an invalid statement. Here it is a valid statement. Next, we will see here, all men are mortal, Socrates is a man, therefore Socrates is a mortal. So here all men are mortal, Socrates is a man, therefore Socrates. So we will have to identify. So how do we identify? All men are mortal, So first thing we will have to denote it. Socrates, he is a man, right? Now we will denote, let m of x be a man. M of x is a man. Mortal, I can represent it to be as some other variable, right? T of x. X is mortal. Then Socrates is a man. All men are mortal. Socrates is a man. So here you will have to identify which is the subject and which is the predicate term. So predicate is man, and here we have Socrates. So Socrates is a man. I can represent it to be as right, let us see, and therefore this should imply, therefore this should imply mortal. Fine. So S represents Socrates, we can have S represents, he is a Socrates. So now coming on to the formation of our premises, all men are mortal, which means that if he is a man, then he is mortal, which means that the quantification used here will be for all x, m of x, conditional, if and then we have got here conditional, if for all x, m of x, conditional, t of x. Then Socrates is a man. Socrates is a man, yes. So x is a man, x is Socrates. So we will have it to be as m of s, right? So therefore this will imply Socrates is mortal, right? Socrates is mortal. How do we say that? Socrates is a subject, so it should be within the parenthesis, so that is yes here. Mortal, it is capital T, right? So this should be our conclusion part. So let us check whether we get that or not. So serial number, statement, then the explanation. So first one, we will take this as it is. For all x, m of x, conditional, t of x. So that is rule P. Then we will have to remove of this quantification symbol universal. So which means that us on 1. Us on 1, we get it to be s. We will have to fix up this variable to some other thing. So we will see here we have s here. So instead of some other thing, we can have it to be as s itself. So m of s, conditional, t of s. Then the third one, we have m of s. So that is rule P. Then the fourth point is that, so you will have to see to that what law can be applied to these 2 points in order to simplify and get the final conclusion part as T of S. So that is whenever we have P and P conditional Q, you get it as Q, which means that it is law of detachment. So I can make use of the law of detachment and I will be getting it to be as T of S. That is detachment on 2 and 3. Detachment on 2 and 3. See here I have got T of S. So that is our conclusion part. So this is how one has to get. So one thing we will have to keep in mind, we first, as soon as a problem is given to us, we will have to identify the keywords. After that we will have to assign the predicate terms, and next we will have to frame the premises along with the conclusion part, and suitably we will have to apply either rule P, rule T or rule CP in order to get the conclusion. So if we could finally arrive with the conclusion part of the problem, then it is a valid statement. So here in this problem, we have arrived at the conclusion as T of S. So the given statement is valid. The given statement is valid. So again here we will have one more example. If an integer is divisible by 10, then it is divisible by 2. If an integer is divisible by 2, then it is divisible by 3. Therefore, integer divisible by 10 is also divisible by 3. We are supposed to check out whether it is a valid statement or an invalid statement. So now let us fix up here the keywords. If an integer is divisible by 10, then it is divisible by 10 is one thing, divisible by 2, divisible by 3. Right? These are the 3 things we have. So let D 10 of x, which means that x is an integer which is divisible by x is divisible by 10. d2 of x, which means that x is divisible by 2. Understood here? 2. If an integer is divisible by 2, then it is, so we will have d3 of x, that is x is divisible by 3. Therefore, the integer divisible by 10 is also divisible by 3. Okay, these are the 3 keywords and we have identified and defined it along with the predicate terms. Now that we will frame the premises for this. If an integer is divisible by 10, then it is divisible by 2, right? If and then. So, therefore, integer, therefore, it should be true for all, right? So, we know that if an integer is divisible by 10, automatically it will also divide it by 2. That is very obvious. So, even though that word is missing out, this is somewhat tricky here. Even though the word for all or for every is missing here, we will have to have the quantification symbol as for all x. So, why should we have it as for all x? It is by default we know that if an integer is divisible by 10, automatically it will also be divisible by 2, right? So, divisible by 10, you can take it as 10, 20, 30 and so on. So, those 10, 20, 30s will also be divisible by 2. So, therefore, it is true for all. So, for all x, if it is an integer which is divisible by d10 of x, then it is divisible by 2. So, d2 of x. This is the premises for the first statement. Then, if an integer is divisible by 2, right? If an integer is divisible by 2, then it is divisible by 3, right? So, if an integer is divisible by 2, then it is divisible. Say for example, 6 divides 2, then also it is divisible by 3. So, it is, if it is an integer which is divisible by 2, then it is divisible by 3. So, this should imply, therefore, means it is the conclusion part, the integer divisible by 10 is also divisible by 3. Therefore, the integer divisible by 10 is also divisible by 3, which means that we have for all x, d10 of x, conditional d3 of x, if and then, right. So, therefore, the integer divisible, fine. So, now we will have the derivation part, statement, explanation. So, first term we will take it as it is for all x, d10 of x, conditional d2 of x. Here it is rule P. Then I will have to remove of this. So, if I remove it, it will be universal specification on 1. So, that we get this to be as d10 of A conditional d2 of A. So, which means that I am pointing out to a specific variable or specific term as A. Then we will have to take for all x, d2 of x, conditional d3 of x, that is rule P. Next is, again we will have to remove of this universal quantification symbol. So, it should be US on 3 also again. So, it will be d2 of A conditional d3 of A. See here, for these two statements, that is second and fourth statement, we have d10 of A conditional d2 of A and d2 of A conditional d3 of A. So, what is the suitable law we can apply on these two steps? So, the law which is suitable is what? It is chain rule. Good. So, chain rule on 2 and 4. So, chain rule on 2 and 4, what do we have here? It is d10 of A conditional d3 of A, right. So now see to the conclusion part, accordingly we will have to write it. So it has been generalized, which means that I will have to have the universal quantification symbol here and generalize it not to a specific point. So which means that UG on 5. So UG on 5 we get it to be as for all x, D10 of x, conditional D3 of x. See to the conclusion part is also the same thing. So therefore we have arrived at the conclusion rightly and hence the statement is valid. The statement is valid. So again we will see few more problems. Show that for all x, P of x or Q of x implies for all x, P of x or existential quantification of x of Q of x. So whenever you just look at this problem, so in this problem we have got only one premises in the left hand side, and with that we are supposed to prove that that is equivalent to the conclusion part, say something else. So whenever we get a problem of this kind, that is only if you have one premises, and with that if you are supposed to get the conclusion part of the problem, what method we can preferably make use is that we can make use of indirect proof. So why we go for indirect proof is that at least minimum if we could have two premises, that is more convenient way. If we have at least minimum of two premises, then somehow we can apply any of the law and then we can get the conclusion part of that given statement. So as far as this problem is considered, never mind even if we can use direct proof also, but the thing is that it will be little bit tedious and we will have to think about it, how do we arrive this. So in order to avoid all those confusions, what we can do is that we can just go by the indirect proof. So why we prefer indirect proof here is that we will be taking negation of the conclusion as also one of the premises, and then finally we must be able to get the conclusion part as F. That will be much more easiest for us to do it. So here we will go by indirect. So far we have done all the problems by direct proof method, and here we will go by indirect. So nothing harm if we make use of direct proof also, still we can make use the easiest way. I am telling you this. So even if you want to go by direct proof, you can go, nothing wrong in that. So now it is serial number, statement, then the explanation part. So here first thing I'll have to take the negation of the conclusion as the first and foremost step, that is negation of P of x or there exists x Q of x. That is negation of conclusion. Conclusion we will be writing. And next step we will have to simplify as far as we can do for this step. So for that I'll be applying the De Morgan's law, right? So we'll apply De Morgan's law on 1. So if we do that way, we get here to be as there exists x not P of x, and this will become and this it will become for all x not Q of x. And then here I will have to somehow remove this quantification symbol also. In two different steps we can do, or simultaneously in one step we can apply both the laws. So for your convenience sake I will do it twice here. So that is first I will remove of this existential quantification, that is I will be saying it is specifically pertaining to only one single object. So therefore ES on 2. So ES on 2 we get this to be as not P of A and for all x not Q of x. Again we will have to remove this quantification also, that is US on 3. So therefore it is negation P of A and negation Q of A, right? So now even I can apply ES and US simultaneously here, since because this is a first problem we are applying both the laws here, it will be confusing you, so that I have done it in two separate steps. So next is conjunctive simplification. I can write this to be as negation P of A or negation Q of A I can write. So this is conjunctive simplification on 4, we get this. And next look into this part, that is for all x P of x or Q of x. That is what it is, rule P, given premises. And again for this also we will have to remove this universal quantifier. So that is US on 7. So US on 7 we get it to be as P of A or Q of A. So our intention is to get the conclusion as F. So however possible you can apply the laws. So now I can apply conditional equivalence on 8. So conditional equivalence on 8, if I apply it, what is that conditional equivalence? Whenever I have P or Q, that is equivalent to not P conditional Q. So that is how I will be applying here. So not P of A, conditional Q of A, right? So now here look at this 5th and 9th step, right? 5th and 9th, I have not P of A, not P of A conditional. So what is a suitable law that we can apply here? Yes, that is law of detachment. So law of detachment on 5 and 9. Law of detachment, what it says that P comma P conditional Q will give us Q. So therefore it will be Q of A. So look into the 6th and 10th, no? We have got Q of A. We will take conjunction of these two, right? Conjunction of 6 and 10. So conjunction of 6 and 10. So what this will give us, it is of the form P and not P. So what is that? It is equivalent to F. So which is F, and that is the contradiction. So in the indirect proof, finally our result should be a contradiction, which we are able to arrive at this point here. So therefore this is proved.